Good morning, everyone. Today we are going to continue our discussion of section 12.3. This is part 2 of our discussion. Yesterday we had talked about limiting and excess reactants, and today we want to go over percent yield. Let's begin with the equation for percent yield. Percent yield is calculated by taking the actual yield divided by the theoretical yield times 100%. All right, let's define what actual yield and theoretical yield are. Actual yield is your experimental value. So when you do the experiment, perform the lab, this is what you actually get in lab. The theoretical yield is the ideal or maximum amount that could be produced. This is something that has to be calculated using stoichiometry and the balanced equation. The best comparison to real life that I could maybe give you is yet another cooking example. So when you buy like a box cake mix, it'll say, you can make one 13 by 9 pan of the cake, or sometimes it'll say you could make like 24 cupcakes. I don't know about you, but when I do that, I hardly ever make exactly 24 cupcakes. Sometimes I get 20, sometimes I get 30 out of it magically, but I don't get the true value that they say you should get. The 24 cupcakes that the label is telling you should get would be like the theoretical yield, all right? So based off of the recipe and what you're starting with, that's what you should get. What I actually make in real life would be the actual yield. Now, I would like to remind you that today you're going to need a calculator, a periodic table, your mole map, if you have one, to help you out. So if you don't have those things available to you, I would pause the video and go get them right now, because we're going to move on and do some example problems. The first example is example number 3 on the sample problems that we were working with yesterday. If you have that sample problem sheet, you're more than welcome to get it out and write along. If not, just follow along and write down the problem as we go. So the problem says chlorobenzene, which is C6H5Cl, is produced according to the equation C6H6 plus Cl2 yields C6H5Cl plus HCl. When 36.8 grams of C6H6 reacts with excess chlorine, 38.8 grams of C6H5Cl is actually produced. What is the percentage yield? All right, this looks a lot like yesterday's problem in that we are given two numbers, but I would like for us to stop and think about what those numbers are. So this 36.8, let me change my colors here. That 36.8 grams is of the C6H6. Meanwhile, the 38.8 grams is of the C6H5Cl, which is a product. Yesterday, when we were given two numbers, we were given two numbers for the reactants. Today, we have a reactant and a product, and they just tell us that the chlorine is in excess. So we need to stop for a second and think about what these numbers are telling us. This 38.8 grams, according to the problem, is the actual yield from lab, and we are supposed to find percent yield. So if we think back, the equation for percent yield said that percent yield is equal to the actual value over the theoretical value times 100%. Now, given the information that we have in the problem, our percent yield would look like this. We know that the actual yield is 38.8 grams of C6H5Cl. Now, a common mistake that I see students make then is they'll say, okay, well, my other number is 36.8 grams of C6H6. So I'll just throw that down there, multiply by 100%, and life will be good. But I want you to take a look for a second at your units. On the bottom, you've got grams of C6H6. On the top, you have a similar but different unit of grams of C6H5Cl. These units have to be the same for percent yield to work out. So we can't take that approach. Instead, let me get my eraser out so I can remove that, since that's clearly not right. I am going to have to do some math, because if I go back here to my definition of theoretical yield, it says that it has to be calculated using stoichiometry and the balanced equation. So what I need to do here is I need to say, if I know, whoops, I need to change to my pencil. If I know that I have 36.8 grams of C6H6, I need to convert that to grams of C6H5Cl that could be made. And if we think back and look back on our mole map, grams to grams conversion is going to be a 3-step conversion. And if I look at my units, the first unit I'm looking to get rid of is grams of C6H6. And I must change that to moles of the same stuff, C6H6. But I don't want an answer that's in moles of C6H6, so I'm going to put that on bottom. And I have to go to moles of C6H5Cl. Now I get that those are pretty similar, but they are different, so pay attention to what you're doing. I don't want an answer that's in moles of C6H5Cl though. I want an answer that's in grams of C6H5Cl. All right, now it's time to go back and put in numbers. So in my first conversion factor, I will put a 1 with moles because it's a grams to moles. Then you need to add up 6 carbons plus 6 hydrogens. So that's going to be 6 times 12.01 for the carbon plus 6 times 1.01. And I have, when you do that, you get a molar mass of 78.12 grams. Now for my mole to mole conversion, I need to go back to my balanced equation. We didn't double check this equation, but I will tell you that if you do double check it, it is in fact balanced. And we have coefficients of 1 for each of those substances. So I'm going to put 1 to 1. Now on my last factor, this is another grams to moles. So I'm going to put a 1 with the moles. And this time I need to add 6 carbons, 5 hydrogens, and 1 chlorine. I have, when you do that, that gives you a mass of 112.56 grams. So I'm going to take 36.8 divided by 78.12 times 1 divided by 1, which won't really change your number, and then multiply by the 112.56. And I have, when you do that you get 53 grams of C6H5Cl. That right there is your theoretical value. That's how much you could make in a perfect world, given the starting amount that you have, the balanced equation, and stoichiometry. So now I need to take that number and put it in the denominator of my percent yield equation. 53 grams of C6H5Cl. Now notice, at this point, my units are the exact same on the top and the bottom of my fraction, which is what I want. So those are going to drop out. So I'm going to take 38.8 divided by 53 times 100. Now I do want to remind you, please do not use the percent button on your calculator. It's going to multiply by 100 another time. So just take 38.8 divided by 53 and multiply it by 100. And I have that when you do that, you get 73.2% yield. Excellent. All right, let's do another problem, because tonight your homework assignment is going to be a continuation of the 12-3 practice problems that we were working with yesterday. So I would like for us to take a look at sample problem number 20 on those 12-3 practice problems. This says, determine the percent yield for the reaction between 6.92 grams of potassium and 4.28 grams of oxygen if 7.36 grams of K2O is produced. We have to begin all of these problems with a balanced equation. So it says that you are reacting potassium and oxygen to make K2O. So let's write a balanced equation. K plus O2 yields K2O. However, that is not balanced. If you look, we've got 2 oxygens on the left and 1 on the right. So I need to put a coefficient of 2 out here to get 2 oxygens. However, now that's given me 4 potassiums on the right and only 1 on the left, so I need to put a 4 on the left side. At this point, my equation is balanced. Now, let's write out what we are given. So they say that we're starting with 6.92 grams of potassium. We also know that we're starting with 4.28 grams of oxygen, and they tell us that we make 7.36 grams of the K2O. That is our actual experimental value from the lab. So we are supposed to find percent yield. And remember, percent yield is the actual over the theoretical times 100%. So I already know the 7.36 grams of K2O. I need to find what the theoretical value is. Now, if I go back and take a look at the sample problem that we had up here, I took the 36.8 grams of reactant that they gave us and turned it into product. However, in the last problem, they gave us one starting value and said the other substance was in excess. That's not the case here because we're given two starting amounts. So we have to figure out which one is the excess reactant. This is like merging what we learned yesterday and what we're learning today. So in order to decide what our theoretical yield is, we are going to have to convert the 6.92 grams of potassium into grams of K2O. But we are also going to have to convert the 4.28 grams of O2 into K2O and see which one is actually possible, which one's our limiting reactant. In both cases, going from grams of one substance to grams of another substance is a three-step conversion. So I'm going to draw in my three conversion factors here. Let's begin with the top problem. So if I have 6.92 grams of potassium, the first unit I'm looking to get rid of is grams of potassium, and I need to change that to moles of potassium. If you need to consult your mole map for how you proceed with your units, absolutely do that. All right, but now that would give me an answer in moles of potassium, and I don't want moles of potassium. So I'm going to put moles of potassium on the bottom, and the mole map says I may now change that to moles of our other substance, which is moles of K2O. I do not want an answer in moles of K2O though, so I'm going to put that on the bottom, and I'm going to put the units of K2O on top. So if I go back and start adding numbers, in the first factor, I would put a 1 with the moles, and then I look up potassium on the periodic table. It has a mass of 39.1. To go from moles to moles, I have to consult my periodic table, a balanced equation. So I look up here and I've got a coefficient of 4 in front of potassium. I have a coefficient of 2 in front of K2O. For my last factor, we go back to grams to moles. So I'm going to put a 1 with moles. Then I need to add up 2 potassiums and 1 oxygen. I have that gives me a value of 94.2 when I do that. So now I'm ready to plug this into my calculator. I'm going to take 6.92 divided by 39.1 times 2 divided by 4 times 94.2. When I do that, I get 8.34 grams of K2O. But before I can certify that that's exactly what I make, I have to check my other starting amount. So if we go down here to this problem with oxygen, the first unit I'm trying to get rid of is grams of O2. And I can change that to moles of O2. But I don't want moles of O2, so I'm going to put that on bottom. And I'm going to put moles of K2O on top. I don't want an answer in moles of K2O though. I would like grams of K2O, so I'm going to put moles of K2O on bottom, grams of K2O on top. So plugging in my numbers, in my first factor I'm going to put a 1 with the moles. Now since this is O2, you have to take 2 times the mass of 16, which is the mass of 1 oxygen. So that's going to be 32 grams in every 1 mole of O2. Then to go moles to moles, I have to look at my balanced equation. There's a coefficient of 1 in front of oxygen and a coefficient of 2 in front of K2O. For this last factor, I put a 1 with moles because it's a grams to moles. And actually, I can just look up here to my last problem where I had already found that there's 94.2 grams in every 1 mole of K2O. So now I'm ready to plug in. I'm going to start with 4.28. I'm going to divide by 32 multiply by 2, and multiply by 94.2, and I get 25.2 grams of K2O. So now we have to decide, what could I make? Could I make this 25.2 grams of K2O or 8.34 grams of K2O? The correct answer is this lower amount. Remember, in limiting and excess reactants, you are always limited to the smaller amount. So that value right there is going to be our theoretical value, which means if we started with 6.92 grams, use just the balanced equation, in a perfect world, we ought to be able to get 8.34 grams of K2O. So what I'm going to do with that now is I'm going to go back and plug that into my percent yield equation. So in the denominator now, I'm going to put that the theoretical value is 8.34 grams of K2O. And again, notice we've got grams of K2O in the top, grams of K2O in the bottom, which is great because then our units will cancel. We're going to multiply by 100%. And I have that this is going to give you an 88.2% yield for this problem. All right, so our takeaways from today's lessons. You still must begin all of these problems with a balanced equation, so make sure you write that out. Then you find your percent yield by taking actual yield over theoretical yield times 100%. The actual yield is what you actually get in the experiment or the lab, and the theoretical yield is something that you have to calculate. It's the ideal or maximum amount, and you calculate it using stoichiometry and the balanced equation.